So yeah, today's talk will be about 6LoWPAN, which is kind of the fundamental thing for the talk on Wednesday, which is co-op. So I actually don't have that much co-op in there. There's just one slide mentioning it and roughly explaining it, what it is about. The thing is, 6LoWPAN is around for quite some time now, so I wasn't sure what to expect, what you already know about it. If something is too long, you already know it, please tell me. If something is too quick, then tell me as well, and yeah, feel free to ask questions in between. Would be nice to keep this interactive and really, yeah, have a nice dialogue on this. So yeah, the topic is low power IP. The thing is, network embedded systems have been around for a long time. So things were deployed during the Vietnam War already. You had a sensor network that was monitoring the Ho Chi Minh path, for instance. And today you have, yeah, deployments like building automation with lots of connected devices. Real-time city information already is coming in. Logistics uses it a lot. Structural health monitoring, smart energy. The thing is, a lot of these deployments are wired. And the really bad thing is they are actually islands, so they are not really connected. So you have this deployment, it serves that purpose, and it's really hard to connect this information with some other information. And what we actually want to have is this Internet of Things. So everything is connected, we can share the data. And the really nice thing that came up in the past few years is we have end-to-end IP connectivity. So we have the small devices. They already speak IP, so it's super easy to bring them into the IT backbone system. So it's super easy to get the data into databases, into processing engines, and so on. So that's basically the goal, to have IP-based Internet of Things. And yeah, 6LoWPAN is a key piece in that. So because it provides basically IPv6 for low power wireless. And yeah, to see what this is about, let's start with a bit of history, where it started, where it came from, and what the challenges and goals are. So back in 2000, yeah, the new idea of smart dust started. So that was started in Berkeley, in California, and the idea was to have really, really small devices. So they actually built it as well. So this is an actual mode that was able to communicate via light. So there were some mirrors to reflect information. And so the big idea was really to have some UAVs that fly around, deploy this, and then you have small sensors deployed over a huge area. They connect to each other and start sending data. What they actually built then to communicate, you see here it's a bit larger. They use the laser pointer to communicate actually over the bay, so the San Francisco Bay, to exchange information. And yeah, it basically started the area of wireless sensor networks. So there was a lot of academic research in that field. So one part was definitely working on sensor node platforms. So on the right you see some examples, the Mika 2 for instance. T-Mode Sky or Toulouse B was one of the most used sensor nodes in research. Mostly because it's pretty convenient to program. It has the USB connector, you plug it in, you can flash it, and that's it, and it connects. And yeah, so to work on this, this whole ecosystem started. So there was also research on event-driven operating systems, because the main challenge is that these things should be cheap. So if you want to have billions of these things thrown out and communicate, they must be really, really cheap. That means that they are really constrained, so you have really small resources. And yeah, they started to work on operating systems to scale down again. So basically, back when computing started, you only had a few kilobytes, then it grew and grew, and you needed like gigabytes of RAM that something works. And now you had to scale down again to make it work in a few kilobytes again. Other things like low power MAC protocols, so to have really efficient networking to get the best out of the batteries. You want to deploy these things and they should run for 10 years, something like that. And yeah, there were experiments, what applications is this actually good for. So there was this big idea, but also they tried to figure out what is it good for, what kind of applications are in there. At the same time, there were also industrial specifications that came up. So one of the more famous one is ZigBee. There's also wireless HART for factory automation, for instance. And they all focused on IEEE 802.15.4. That was a specification that came out in 2003, and was a really cheap, low-power chip. So it started at ChipCon, and the company was bought by Texas Instruments, and they produced this CC2420, which is the radio chip that was used in this research. And you had these protocols, they had to be highly efficient and so on, but again, you had these islands, so actually every application was created from scratch with new protocols and specially designed protocols, and that didn't last long. Each deployment was there. Once they were finished, they saw, okay, it's hard to integrate this. And actually already in 2003 there was this proposal, let's use IP for this. It's much easier to integrate this. So it were the pioneers, for instance, Adam Bankholz had a paper 2003 about this full TCP IP for 8-bit architectures. A bit of fun fact, so this is based on Contiki. Contiki was actually retro computing. So what he did in his free time was to implement a web server with a full TCP IP stack on his C64. And that's where Contiki came from. And there are still a lot of people in the Contiki community to do retro computing. And the other one is Zach Shelby. He had actually a paper in the same year, just a few months later at a different conference, and proposed nano-IP, so basically the same thing, have IPv4 in that case for wireless sensor networks or these network embedded systems in general. And only a few years later the official effort started to really standardize this, so there was a new working group chartered in the IETF for 6LoWPAN, so this is IPv6 for these low-power wireless personal area networks. That's the name that comes from this 15.4 standard for the physical and MAC layer. So that's why there's this pretty ugly name, 6LoWPAN. And only a year later you had the first RFC that described how you get IPv6 cut down to these small devices and have this low-power IP. The big major paper was 2008. By Hugh and Color, both again from Berkeley, where all this started. IP is dead, long live IP for wireless sensor networks, and they had the first really comprehensive implementation where they also looked at other issues. It's not just the format you need, you also need to route and communicate and so on. So that's what they looked into, and then there were some other amendments to the initial RFC. For instance, there was an update on the header compression, so what else you can do to be a bit more flexible. And another important thing, the routing protocol, Ripple. So it's called Routing Protocol for Low Power Lossy Networks. And the last RFC was actually only 2 years ago with a neighbor discovery for 6LoWPAN. So it's a bit different than the standard IPv6 neighbor discovery. So now in 2014, what we have is actually this is pretty well working. There are a lot of companies that use that sell that have a lot of products based on this. And this is actually really pushing forward the idea of the Internet of Things, because now we really can use the Internet to connect all these things. So with the background where we started, I want to give some basics so you can understand what's actually in there on this. So what 6LoWPAN creates is so-called edge networks. So you have your normal network, for instance, you have the Internet, with a router you're connected to the Internet, and you have your local area network where your normal PCs and so on are connected, and on this backbone you put the border router. So the name already says it, it's the border of that thing, it's an edge, and behind that you have this LoWPAN or 6LoWPAN with the low power communication. So to really let's look at the stack first. So you want to have IP because this is for big numbers of new devices in the internet, and they focus on IPv6. So much more addresses and so on. This is how usually a stack would look like. So at the physical layer, you have this 802.15.4. What you need is some kind of rate duty cycling. That means that you can save energy to have a longer battery lifetime. So you have to do some clever things when to use the radio and not. So there's the standard amendment 15.4e, for instance, or there are some other protocols that are basically shipped with the operating systems you can use in the field, like Contiki Mac, or there's also AMAC or TinyOS, which is a different operating system for these kind of devices. Yeah, you have the normal media access protocol, CSMA for instance. Then you have this adaptation layer before the actual IPv6 comes. And on top, currently actually there's only a definition for UDP, because also in this paper I mentioned, it turned out that TCP performs pretty bad on these low power links. You have multi-hop communication, you have a lot of drops, so packet losses. So TCP yeah, doesn't perform that well as it should be, and it also eats up a lot of memory in your implementation. And yeah, so UDP, so usually you have CoAP, that's a new application protocol based on that on top, but we're going to focus on this adaptation layer 6LoWPAN. So this is how a normal IPv6 and UDP header would look like. Don't read the specifics, it's just the header format you find in the specification. The thing is, you have two really big blocks there, and that's just the IPv6 addresses there. 128 bits, so that's already 16 bytes twice, and all in all you got 48 bytes just for the header to transport some useful information. And yeah, that must be compressed to actually use this low power communication. And to understand how this can be compressed, let's look at the addressing scheme, how this is done in IPv6. So from the internet, from the ISP, you get the prefix. So that's everything that starts with this prefix will be routed, for instance, to your router, and then you are in charge of distributing it further. So we start with a /48, so that means 48 bits are fixed in this prefix address, and then you can create other longer prefixes, for instance with 64 bits, which is kind of the subnet from IPv4. You know, so you would give one of these prefixes to your backbone, the local area network, and also the LoWPAN would get its own prefix. And then how the actual address is configured, so there's no DHCP, so you can have DHCP as well, but what you can do is have some kind of auto configuration. Just take the prefix, the 64 bits, and then put the so-called EUI64, concatenate those, and that gives you your full IPv6 address. And this 64-bit EUI is actually the MAC address, so new devices don't have a 48-bit MAC address, but a 64-bit MAC address. And yeah, just putting them together automatically without any configuration, without any special doing, gives you the full address. The point is, the MAC address is in there in the IPv6 address. So what 6LoWPAN does is basically a stateless header compression, because there's so much redundancy in the header. So originally, it would look like this. So, the whole thing is a frame you have at 15.4, and more than half of it would only be header. So this is all header, and this part is only a payload, so 53 bytes left, and that's not very efficient. So that's why 6LoWPAN comes into play and can reduce it to just 6 bytes, for instance. The thing is, you already have the MAC headers, which include part of your IP address, so you can just reuse this information. You have length information you can reuse, and all this redundancy is basically removed. You have some fixed bitmaps that indicate, okay, this is the case, just take this information from there, and if there's something you cannot really compress and include, you just add it behind here, but still end up with a much smaller header. The thing is, if you look in the bits and bytes, it gets really complicated, because it's really there's kind of a lookup table, and if this is the case, do this and use the next byte and whatsoever. So this results that the exact header is actually always in a different length depending on the situation you have. Whether you have a link local address, so for instance you can just, okay, this other node is in the same subnet, it has the same prefix, so I don't need the prefix, I don't have to send it. If this is a global address somewhere across the internet, then of course you need this full address. And that's why you end up with different schemes. This is just a picture I took to give you an impression that, there are many cases, and the details, are a bit ugly. You're happy once you have implemented this, and then better not touch this again. And it can be confusing if you do measurements. and want to know what's the header, don't be confused if yeah, you happen to work with this and you get different numbers. That's part of the scheme. And yeah, it can actually get more confusing. So for instance, if you have well-known contexts, so for instance, you're always communicating with this one address over there, you can just define this as a context, use a few bits to say, okay, this is this remote address, and then there's a lookup, and you don't have to encode this full address every time. You just say, okay, this belongs to this context, and then the border router can add this information later. Maybe if I wasn't that clear, the border router does all this work to actually blow up to the full header again. So something comes from the internet with the full headers, the border router then applies 6LoWPAN compression, and the smaller headers go down into the LoWPAN, and the other way around if you want to go from the LoWPAN to the internet. So we have the compression, and the other big thing you need is fragmentation. So the minimal maximum transmission unit of IPv6 is already 1280 bytes, which is already kind of 10 times longer than the frame size you have in low power communication. So the other big feature about 6LoWPAN is slicing up this MTU and fragment it over multiple frames to transport one IP packet to your node. So this was basically what 6LoWPAN does. So it's basically a scheme to compress the headers and adapt it to the small frame sizes of low power wireless communication. So I said 6LoWPAN and Co, because there are also some complementary protocols in there that you need to actually make this work. And one big thing is routing. How should this be done? So the thing is, you have multi-hop communication, so it's not like Wi-Fi where you have one access point and then just a star topology and one hop, but you have multi-hop communication, so it could be multiple hops until you reach your host. So what you need there is routing, how to forward this. And one way to do this is the so-called route over technique. So you have your 6LoWPAN and then do the routing over this network layer. And for that, the border router creates a so-called DODAG. That's a direction-oriented, directed acyclic graph. You have to read the RIPFOL specification, so that RFC has, I think, 10 or 20 offers, and is super long and super confusing, and you can already see that at this DODAG acronym. So what actually happens is that every node in your LoWPAN is a router, or most of them are routers, so they can do routing, and only a few leaves are hosts. If they are smaller devices, for instance, they don't need to implement that. Then that also means that they cannot forward any packets. And what they do to scale this up, so imagine you have thousands of nodes in this multi-hop node network, you cannot store the full routing table, just not possible in a few kilobytes of RAM. So what they do is source routing. So once this guy wants to communicate with that guy, it doesn't have an entry for that, so okay, default route, and it goes up to the parent. The same for the next parent, until it actually ends up at the border router, which is unconstrained and basically has the full routing table for all devices in the network. And that one then can again tell in the header, okay, this has to go down this route, and finally you can deliver it to the other node. You can improve that. Sometimes it can be really bad if you have real-time applications, actuation and so on, and want to have a short delay time between that. There's a so-called storing mode for RIPFOL, and that basically means that the routers in the network also have routing table for all their children, and can then forward directly to these nodes, and it doesn't have to go all the way up to the border router. And this thing is also important if you want to implement multicast. There's this storing mode for RIPFOL. It's a multicast protocol for low power and lossy networks. And yeah, just to duplicate, otherwise you end up with a full flush and every node, so it would be a broadcast if you don't have this information in the intermediary nodes. And you can do yet another thing, so if there are multiple flows of information in your LoWPAN, you can even have multiple of these DODAGs around, so that overlay, and then yeah, you can do peer-to-peer routing basically, but then you need more and more memory again to actually implement all this.
And what does happen when in all the routing scenarios when one of the nodes is sleeping?
So this is I didn't cover this topic. So there are these two really different approaches. So there are these so-called sleepy nodes, and the other thing I was talking about is radio duty cycling. This radio duty cycling is what is usually used in this kind of research at this setup, and they are virtually always on. I have a few slides to radio duty cycling, how it works, and then they can sleep a lot, but they are virtually always on. So if you have really sleepy nodes, so basically where the application decides when this guy should wake up, you would implement it as a host, so then it doesn't participate in routing.
It's almost the same question, but a little different. What happens if a node moves, or every node moves in this scenario? That the problem, I don't know if they have a lot of memory to store the DODAG first, and secondly, the DODAG update may take some time.
Yes, so
there are some techniques to simplify this process.
yeah, so maintaining these graphs or trees is really, that's the overhead, that's what you have to pay for. The thing is actually a quite important thing, what you can see here. What Ripple does, it maintains multiple parents. So for instance, if this node fails, is mobile or whatsoever, you recognize this because they don't get the acknowledgements and so on, and then you switch to the next parent and then use this to forward this information. So you always keep as many links to parents in memory as you can afford, and they are basically complex metrics how to decide which parent you take. So there are different objective functions that you can use. They also have fancy names like Mr. Hoff. And more complex one, I think the other one is just object function 0. So yeah, that's how we decide where to send it. So this whole thing is actually based on the collection tree protocol, which was a converge cast protocol. So you have just a lot of nodes that send information, and that has to go to a sync node. And you want to have really high packet delivery ratios. And based on that is actually Ripple. So as you see with the source routing, it's more get everything to the sync node and get it there with high probability or with only a few losses. So that was the one thing, the route over. So you have to implement routing. The other version is mesh under, because for instance, Zigbee defined mesh networks, or it's basically a complete different research area where you have mesh networking. And what it means basically is you know all your neighbors in range, and then can have really a lot of routes to reach a different node. So they're somehow all connected. There are things like ad hoc, on-demand, distance, vector, so other routing protocols that can do that. The thing is, so for IP, it's hidden or they're connected. It just looks like it's one local link, like Ethernet plug-in through a switch or whatsoever. And the difference here, or the part that was amended through 6LoWPAN MD, is that the border router is also a whiteboard. So every node that is in the network checks in there, registers there, and is known. So you can do duplicate address detection. So if you generate addresses, for instance, or configure them hard-coded, you can detect that. You can generate short addresses. That's something for 15.4. For this specification, you can either have the full 64-bit addressing or 16-bit short addressing, which again saves a lot of space, and that this translation you can do with this whiteboard. It's basically for lookups from outside the network. So if you want to know, is there a neighbor, so a neighbor solicitation, If you do that, you can ask the whiteboard and you don't have to wake up node, for instance. You still know it's there, it's registered. And you can also support mobility actually, so that one node moves from one LoWPAN to the other. Okay, the second part, I already mentioned it, is ready duty cycling, what you need to make low power IP work. This is an overview how energy is spent in normal operation on the sensor node. So the absolute numbers come from this T-mode Sky, which is often used, as I said. You see the two big things. So one is radio, and that's the actual problem. Your phone is writing the flash, but that's nothing you would often do. So sometimes there's a firmware upgrade or whatsoever, but that's not normal operation. So you really have to take care about the radio energy consumption. So interesting what you see here, for instance, receiving is even more expensive than sending. In this case, for this radio chip, it's because of the low noise amplifiers that need more energy than sending the symbols, where you only have to have short pulses to generate the symbol. And I think in newer generations they could change this again, but this is more that they send with more power to have less losses actually. So what do you do? So one approach is Contiki Mag, which achieves really low duty cycles. So low duty cycles is all below 1% of the time the radio is actually on. Default configuration is something like 0.3% for Contiki Mag. And what it does, you have the receiver, and it does periodic channel checks. So you see two bars here. It's because it checks, is there energy on the channel? And after a short time it checks again, because there could also be just one spike because of noise. So you have these two checks and do this periodically. Basically, is there someone sending? Should I listen in? And if the sender wants to send something, it just switches on the radio and starts strobing basically the data packet. And at some point, this packet will fit to the channel check. With the second check, oh, there's still energy there. It knows, okay, there's something going on. I keep my radio on, and it's ready to receive. We'll send an echo that thing, and then the sender knows, okay, this was received. I can stop transmitting. Something we also worked on were so-called link layer bursts. There's something like a frame pending bit in the specification of 15.4. You can set that, there will be a next frame, and you can use that once you know this is set, I will just keep my receiver on longer, and then you can send a train like this. You need multiple frames. There's a bigger IP packet, it's fragmented, but you can send it in one burst, which saves you time, because you always would have to wait these cycles. And that's actually how you pay for this energy save. So on the one side you have energy. So if you don't have duty cycling, it's the gray bars what you have to spend. If you turn radio duty cycling on, you see it's much less energy you spend. However, on the other side you see how you pay because of latency. You always have to wait until the next guy wakes up, and if you have multiple hops, of course this sums up. So that's trading energy for latency. So that's already my last part of the talk. What's going on currently? So since this was specified, 6LoWPAN and so on, there were some other works to improve on that. So what's the state of the art? Cisco had a test deployment for Ripple, where they connected 16,000 nodes in a single Ripple multi-hop network. The idea was basically to use this for smart metering. You might have heard Zigbee IP, the term. So Zigbee, which started with their own protocol stack and so on, also switched over to using IP. And there was the plan of basically this smart energy profile to use this, and that's what they worked on. The smart energy profile got a bit stuck, so there's not that much effort in it, but Zigbee IP is supposed to be one specification how you should configure your IP stacks, and to make it interoperable, so you can have this, okay, it's Zigbee IP sticker, and then different protocols you might need are available, and you can rely on that. Reliability, speaking of it, what you can achieve is more than 99% delivery ratios. Although you have lossy links in this environment, there are some new results from research, like the low-power wireless bus, for instance, was developed at some colleagues at ETH Zurich in the electrical engineering department. What they use is the capture effect and constructive interference to flood the whole network. So if you have multi-hop communication, if you do the timing right, it must be within half a microsecond, you can just overlap the sending wave, and you can go in waves to really flush this in a few milliseconds, and basically have this feeling of a bus. You have a multi-hop communication, but it's just you put it on the bus and everyone can read this information. This could be interesting for this mesh under technique for 6LoWPAN. The other thing, you can combine Ripple, for instance, with Contiki-Mac. So you just listen and opportunistically receive something and just forward it again. And measurements show that with that you are much more efficient and also much more reliable. And then the last thing is this 6-ish working group in the IETF, which is basically about time scheduling and channel hopping. So you do not only use one channel, but you hop around the channels a bit like Bluetooth, if you know how that works, to mitigate narrow narrowband interference. And time scheduling, because it helps you, you can assign specific slots to this node. This slot has to send a lot of data, so it receives more slots. And that's why it gets more reliable. And as I said, in terms of efficiency, because you have this really low duty cycle, you get battery lifetimes of years now. There are these academic protocols, but there's also the 15.4e amendment that standardizes that. I'm still waiting that they kind of just put this in the chip, that you can rely on that and don't have to do this in software, because the problem is this is really timing sensitive, and usually an implementation just works for this platform where the delays from the microcontroller to the radio or whatsoever are like this. So it's really hard to port this, so it's nice if you really have a system on a chip and basically have this implemented directly in the radio front end to get the good timings. And then also it's good if you have it in hardware, then you are probably interoperable and no one can mess it up in software. So there's still a continuation of 6LoWPAN. They shortened it, now it's only 6Low, the working group name. What they basically do is porting this binding to other radio technologies. So far it's only 802.15.4. What's in the pipeline is Bluetooth Low Energy, to have a binding for that. It's also interesting because you only have 27 bytes per frame to send data, so the fragmentation must be even more aggressive. There's this ITUT standard. It's kind of compatible with Z-Wave. And then DACT Ultra Low Energy, DACT ULE is also in the pipeline. What this basically boils down to is a proposal for generic header compression, so that you don't have to do this over and over again for every new technology that comes in there. As I said, at the moment it's really bits, and if this bit is set and this is not and this is, it's a lookup table. You have to do this, and just to make it easier and easier to port to new technologies. There's this draft on generic header compression. Maybe something interesting for Bluetooth 4.1, there's multi-hop or mesh networking coming up for Bluetooth Low Energy, which is quite interesting because Bluetooth, there's this interest group, and they make it really fast to disseminate the technology to really cheaply produce the front ends and so on. So this could be really interesting. This is the slide on co-op. So this is what I'm actually working on in my PhD. It's about building the application layer for this Internet of Things. So far we only have IP end-to-end connectivity, but the applications still are not able to talk to each other because you still need the application layer protocol. And co-op is basically web-based. You reuse the patterns from the web, RESTful communication to be as scalable, as flexible, and so on. And also I make the point of usability, that it actually gets easy to implement network embedded systems, because before it was really, really hard to actually get something done. So the idea is, connect the easiness of web scripting with these small IoT devices. And to finish, so the next big thing I see, which will be interesting or will be the big next step, is security. So interoperable and scalable security for all these small devices. So that means we need public key cryptography on these small constrained devices. There's a good chance with elliptic curve cryptography, so ECC, to actually manage that. So it's much more efficient than RSA. And a nice thing you see that the system on the chips actually have a hardware acceleration engine to speed up the computation. For instance, if you do this in software on an AVR 8-bit microcontroller, it can take like 30 seconds for computation. So, and that's too long with the timeouts and so on. You still have to send. And yeah, to make this work, there's DTLS, which is a datagram version of transport layer security, which is basically used mostly by CoAP to secure this. So you have the standard TLS thing, and yeah, the plan is to have a specific profile what to implement that this is actually interoperable, because you cannot implement everything. TLS is huge. You have so many different cipher suits. It's just the framework basically to what you can do, and this has to be narrowed down that it actually fits on the constrained devices. So there's this DICE working group, DTLS in constrained environments. They also try to work on secure multicast, but that's really complicated. So they started off with the frame format from DTLS, but recently there were some critiques from people from the security area. So yeah, let's see how this works out, that we can actually have this group communication, but then also secure. And authentication of authorization in constrained environments, so basically OAuth for these small devices is also a big thing, yeah, which is currently worked on in the ACE working group in the IETF. And that concludes my talk. Thank you for listening. And yeah, if you have any questions, I'm around longer. I saw a nice buffet out there, so I'm happy to answer your questions.
Just a quick question regarding security. You talked about source routing in slide about routing, and IP, source routing and IP is a kind of security breach, because you can put a man in the middle to sniff packets when you get source routing. So does it include any security issue in the protocol itself, or do you know if there is a risk using source routing in that case?
It's not different from the internet, so that's also why you want to have end-to-end security. So you have the classic multiple layers, so you need layer 2 security, so like protecting your Wi-Fi with WPS. And yeah, that's what you also do for 6LoWPAN, for instance. So you have AES encryption down there, and DTLS is again transport layer security. So you really encrypt whatever application data you send. There are some other approaches. You can have an optimized version of IPsec, for instance, if you want to have some kind of tunneling. If you trust your local network, you don't trust these things. But you're right, it wouldn't work with layer 2 security only.
Yes, from what I know, close to nothing to 6LoWPAN, but from what I've seen, it's a large, complex specification that addresses a lot of subjects, transport, like addressing. In fact, I feel like they are trying to address everything that's been done right and sometimes wrong, and try to fix it, about RESTful APIs, HTTP headers, boxing, and this kind of stuff. And I'm a bit concerned about the versioning and the compliance of all that stuff. I mean, there will probably be some kind of incompatibility, especially if you have some parts that are hardware, that rely heavily on hardware implementation. So, what is your knowledge about this process of the 6LoWPAN next versioning and evolution.
So I'm not aware about versioning, so that every year there will be a new thing. What they basically did, they had their use cases and then looked at, okay, what do we need from all the protocols that are out there, and put something together. For instance, bootstrapping is still a problem. So if you look at that, you find a lot of protocol for you want to join the network, but then you need a trust center somewhere, but then there's only multi-hop communication, so you need to set up a tunnel to get permission to join the network and so on. So there are a lot of different protocols in there, and they cover now, okay, this is what we need for, let's say, 5 applications or use cases, and it's a start to know, okay, I need to implement this, and then we get 80% covered, let's say. If you really optimize this and so on, then of course you might need adaptations. You cannot afford to implement this as well. Well, then you don't have the sticker, you don't implement everything. It has to grow step by step. So what we now need is bigger deployments. The thing is, what this standardization also brings by is that things become cheaper because you can mass produce them. So you don't have these small silos things which have been very expensive. So if there's the standard technology, you can apply this to many different domains. So hardware becomes cheaper, you have software out there that is available, and the integration cost, that's the main problem, or has been the main problem, becomes cheaper. So it's easier to deploy this in building automation, in factory automation, and these different scenarios. But it has to evolve and evolve, and the thing is, this is transferred from the internet. That's why we went there, because the internet evolved as well and had to adapt to new use cases, to new technology, higher bandwidths, and so on. That's at the networking layer, and the same is at the application layer. So that's where the web proved best so far. It is has this loose coupling. Endpoints can evolve independently without breaking the application, and we need something like this also in the Internet of Things. Because you cannot foresee what will be needed in the future, but it was the same for the internet, and this is the architecture that proved best so far. So I don't know whether we can do better.
Yes. My main point was that CLoWPAN is a kind of a wall, as it is written right now, whereas the internet standards are smaller pieces of independently growing specification. That was my main concern about this. If you take something as a whole, it will be harder to make it evolve as a whole as well. But as you said, maybe with high volume production and some kind of factor for things. So I'm using a bit my English. Yes, maybe if we can foresee for a few years I'm speaking in terms of security and cryptography, which every weakness in the specification or trait that you can find is a disaster.
Yeah, definitely. But yeah, it's a starting point. You have to start somewhere, and if you find enough people who will opt in and do this, it gets us forward. I mean, the really big problem is if you really want to deploy this and, I don't know, put it into concrete and then it's in there and has to work for 20 years, we really have to think about the life cycle about these devices, how to shut them off. Certificates and these public keys are a good option. The problem is if you have billions or trillions of devices, if you have a revocation list, that could become really big.
Another question? Yeah. If I want to play with 6LoWPAN at home, or what device I have to buy? I mean, Raspberry Pi, Arduino. Is there Arduino Shield with Wi-Fi and 6LoWPAN and so on? So, what could I do?
yeah, it's even for me a hard topic to find a good hardware platform to play with. Currently, what I ordered was the Open Mode. It's openmode.com or .org. You can check that. It has this CC2538 system on a chip on it, which also comes with this crypto accelerator. And yeah, it's an open source platform, so you can also get the schematics. It has this XP connector, so it's compliant with what you often see in Arduinos. And
so you run Contiki on it, or it's...
You can, so there are several software things as well. So I plan to run Contiki. The things were ported into this system on a chip. They had this Texas Instrument development kit for the 2538. So it works for that. There's the Open Mode, Open WSN implementation, which is basically the foundation for open source 6-fish. So it's from Berkeley, they developed that. It comes with co-op and also some Python libraries to communicate with that. You basically have to look around so that the modes, this T-mode Sky, is incredibly expensive. One thing is there's a sensor, this combined humidity and temperature sensor, which alone costs $20 or $30, and the whole thing is at $150. Still, you have to invest like $50. The cheapest I found were some AVR modules for less, or around 10 euros from Dresden Electronic. The nice thing was that they have a nice footprint. They are about this size, and they have small pin headers, so it's easy to just connect different sensors. So they are small enough that you can build real prototypes. So much better than the rather big T-mode Sky. And yeah, you have to look around what's your use case. The trade-off is also always how much memory do you need, what kind of toolchain supply do you have, how much is the program. And the thing is, if you want to have the JTAG for these Atmel things, that's $400 or $500. You can go cheaper with the ISP, but yeah, it's hard. Maybe I can give you some address if you're interested. So a good playground for 6LoWPAN is definitely Contiki. I prefer it over TinyOS because it's just C, so it's really easy to port it to a different platform, to just connect something to an I/O port, and it's much harder, in my opinion, for TinyOS, where you have an abstraction layer between and then do some VHDL like wiring and then compile it together and then get the binary out of it. So the plain C model is something nice if you really want to play and solder and so on. And Contiki has a good coverage of this whole low-power IP stuff. It's sometimes not fully RFC compliant, but yeah, there are quite some efforts to improve on that. And yeah, it's open source and for that really great.
I wonder what you asked what was the best platform. Above all, we've all seen this. It is Commodore 64, of course. Oh, by the way, can you show me the slide with the Commodore 64? Yes. It was at the very beginning. I'm a big fan of retro computing and gaming, and that's why. So, thinking about 6LoWPAN and IoT and seeing Commodore 64 is wonderful.
Can also just send you the slide that you don't have these cards.
You have talked about smart measuring, but do you know any other example of 6LoWPAN deployment in commercial or industrial applications?
I know that also a French company, Vateco, uses it. They actually use Contiki to build their product, so they have all kinds of sensors for building automation, for instance. They also have these smart power outlets where you can measure individual plugs. The thing is, what you really can buy, usually, it always takes like 10 years until you find this in products. So it took really long to get Zigbee, I don't know, plugs now to buy in the store or in the hardware store or whatsoever. It really depends. Sometimes they don't do it in the open. So I know For instance, Los Angeles is getting some 6LoWPAN co-op-based lighting system, so all the lighting system for LA. And yeah, they're smaller projects that use it. So for factory automation, for instance, there's also the trend to go there, especially in combination with this 6-dish draft that is out there. So so we are not fully there at this complete Internet of Things, everything is connected with everything, which might be a good idea. There was this Watch Dogs games, if someone played that. The thing is, if you have, as I said, the same arguments from before, so if you have this technology, it becomes cheaper and more usable, that's the main point, and easier to integrate all this. It's good if you can deploy this in just your one factory, and you don't need to really connect it to the internet. Internally, the protocols have to work, and there you find yeah, more and more projects.
Just to answer, there is a French startup named Kivivo, which is based in Nantes, northern west France, and they are using 6LoWPAN to connect the thermostat in the home to the internet box, in fact. And you can buy their products in order to control remotely your heating capabilities from your smartphone.
Yeah, there's also one in Germany. In fact, I just remembered that they also built on Contiki, I think. Philips Hue is, I think, also based on that. Then there's this Li-Fi, something like that. They use Wi-Fi, but they also have a version with 6LoWPAN. So it's mostly the startups you find with more innovation that use that. It's not the big ones that roll it up. Although ArchRock, I think, they got bought by Cisco. They had this for building automation. So that's a spin-off basically from Berkeley, which commercialized on 6LoWPAN really early, and they got bought by Cisco and concentrated on building automation and these kinds of things.
I wanted to ask you about the co-op and the open mode. You told something like co-op was integrated on the open mode, but how? Is it a middleware on the top of the stack, or how? Which functionality was implemented on this embedded device?
So, so there's this open mode, so it's basically a company to produce the hardware, and then there's the Open WSN project from UC Berkeley, and they kind of built the whole stack. So they started from scratch from 6-dish, so this time scheduling and channel hopping and so on. They have 6LoWPAN in there, and they have a co-op implementation, and that's in this Open WSN software stack. I mean, there's also co-op for Contiki, you can flash on that. TinyOS supports that, you can definitely port this, maybe with some more effort on this platform.
Okay, and do you have an idea of the size of the application in the embedded?
Yeah, well, so it works on a T-Mode Sky, which has 48 kilobytes of ROM. That's the full IP stack and application and a few application resources. So if you take the full functioning co-op implementation from Contiki, for instance, you are at rather large 10 kilobytes. The thing is, it really implements everything. So every option, everything you can have, and it has spends like 3 kilobytes, I would say, on convenience, that you have a kind of a RESTful framework looking API for that you just implement resource handlers, and then you don't have to care about the rest. So that's more expensive, but you can boil this down to a few kilobytes co-op implementation. And then, again, the thing, it's a huge spectrum. It depends how much you can implement. Co-op, for instance, was designed to be very, very modular, that you can spend as much as you need or as much as you can. But usually maybe this is good. This all is planned for so-called class 1 nodes, which have about 10 kilobytes of RAM and 100 kilobytes of ROM. So that's the target. those devices will probably need these crypto accelerators for DTLS handshakes. But yeah, that's where it starts. Probably the rollout will be a bit larger devices with, I don't know, 64K RAM and 200 kilobytes ROM.
Then the co-op application takes only 10 kilobytes.
Yeah, so the protocol stack with every feature is currently at roughly 10 kilobytes.
Okay.
But that's already with a lot of convenience, glue code and so on.